Imagine a future where clinicians, researchers, and data scientists from around the world are one click away from having access to advanced technologies such as machine learning and medical imaging, and they are able to collaborate on a global scale to solve the most pressing problems in healthcare. My name is Razvan Jonasek. I'm the technical leader for Amazon AWS in healthcare for Europe, Middle East, and Africa. And I'm joined today by Professor Bram van Ginneken from the Radboud University Medical Center. And today, we're going to tell you the story of reinventing medical imaging workloads with machine learning on AWS. So first, I will share with you what problems our customers are facing in the medical imaging space and how can AWS help. Professor van Ginneken will share with you his personal experience during the pandemic and how his team, together with researchers and clinicians from around the world, worked to develop new ways of diagnosing COVID-19 using imaging, machine learning, and AWS. Lastly, I would open the hood for you and show you what type of technologies and architectures you might want to use to reinvent your own medical imaging workloads on AWS. So when I meet with radiologists from around the world, they all want to talk about how can they better serve their patients. Today, they have access to more data than ever before. And the data continues to grow, not just in volume, but also variety and velocity. And really the challenge becomes in managing the data in a cost-optimized way, and at the same time, unlock the value from the data. But doing this with manual processes is just not feasible, nor it is scalable. Plus, many of the radiologists that I talk to, they are already overloaded with work, and there's really no time for it. So technology must help and must be the answer. Though the reality is that our IT colleagues working for hospitals, for healthcare providers, and healthcare systems need to spend most of their time and budget to keep the lights on. And there's little left for modernizing applications and adopting new technologies. And still, while business processes in the healthcare system are being digitized, we all need to remember that information security and compliance is priority number one. So how can AWS support organizations like yours to tackle those challenges? It starts by breaking the cycle of large risky capital purchases and guessing capacity. With a cloud on-demand and utility model, you gain flexibility, you gain agility, faster cycles, and the possibility to use data-driven decision-making in the daily operations. As the sheer volume of data grows, many customers are looking to take advantage of the hyperscale storage available in the cloud, and at the same time save cost with automated optimized lifecycle management. Now, speaking as a machine learning scientist, I know that AI and ML models have proven to be the right technologies to solve many of the healthcare problems out there. And the AWS cloud is not just the place to train and build those models, but more importantly, from a healthcare system perspective, the place where those models can be deployed in clinical production and at scale. Today, people like you and me, clinical professionals, researchers around the world are forced to work from home. So they are looking at using the cloud to really run enterprise imaging and be able to access remotely solutions like PACS viewers and RISs and EMRs. And another way and learning that I had from the pandemic and from this crisis is how hugely important it is for the world to come together, collaborate globally, exchange data securely and in compliance to fight the pandemic outbreak. And this is a good time to hand over to Professor Bram van Ginneken to tell you his fascinating story of fighting COVID-19. The stage is yours.
My name is Bram van Ginneken. I'm a professor at Radboud University Medical Center in the Netherlands. I lead a group on medical image analysis at the radiology department. In 2007, I organized the first grand challenge or competition for medical image analysis. In these challenges, you compare algorithms for a certain task, say liver segmentation in a CT scan. But you do that in a fair manner, using the same test data and the same evaluation protocol for each algorithm. In 2012, we released our platform, grandchallenge.org. Our goal was to make it easy for groups to set up and organize these challenges and keep them running for many years. I will now give a demo of the system. So here we are at the homepage of grandchallenge.org, and we go to the challenges, and you see here a list of all challenges that we know of. So you see that we have 233 of these challenges listed here. And they are on all sorts of topics in radiology and pathology. Now let's scroll down and open a particular one. This challenge is about detecting rib fractures in CT, and it was organized in conjunction with MICCAI 2020. So you see a number of pages that describe what you need to do, and there's a challenge leaderboard where you can see the results of all the teams that have participated. You see the metric here, the detection FRC score, but there are actually multiple metrics. You can configure this system any way you want. You can also click on the names of the people who are listed on the leaderboard to find out more about them. Here's, for example, one user, somebody from China, and he's participating in this rib fracture challenge, but also participating in another challenge called Lola 11. Now, this is a challenge that I organized. I'm administrator, and it's about lung and lobe segmentation in CT scans. And you can see that next to the other pages, we now have an admin page, and that is visible because I'm logged into the system, and I'm the administrator. And you can see my profile. You see all the activities that I'm doing on the platform. You see a lot of these logs, meaning that these are only accessible to me. So we also use this privately in my group. And then as an admin, I can control everything about the challenge, how it looks like. For example, I can edit the pages. So underwater, this is a Django application, so you can edit the pages and it's immediately reflected on the site. As an administrator, I can also control the evaluation. So we're using automated evaluation. You create a Docker container that runs and computes the score for every participant that uploads a result to this challenge. And this is a container is something that you need to prepare if you want to build a challenge, and for that we provide a package on GitHub called evalutils, which contains all the code you need to create such a container. Now let's look at the homepage of Grand Challenge. We have some statistics there, an explanation about the platform, and you can see that over 45,000 people have an account on the platform, and there's almost 200 challenges running on the platform, and you can drill down into it, see how many users are from which countries, the total number of users, and you see that about 2,000 people log in every month to do something on the platform. You see the most popular challenges, how many automated evaluations we have. We've processed almost 40,000 submissions, and you can see always what was the last submission made, in this case to a particular challenge called Learn to Reg. But what we found was that the focus on just challenges was too narrow. What we basically needed in my research group, but in fact in the whole research community at large, is an integrated global infrastructure to develop machine learning solutions for medical imaging. It's not only algorithm development and viewing the results on a leaderboard, we also want to view the scans themselves. So we decided to implement all these steps in grandchallenge.org, and we use this now in my research group for every project we do. That means that we also collect the data in this online platform, and we do the data annotation, and we carry out reader study. Reader studies are basically a study where you compare how well human experts perform a task. So we can compare the human experts with the computer algorithms. And we also put the computer algorithms as Docker containers on the platform so that they can be reused on new data. So if the user of a platform is the radiologist, he can upload new scans to be processed by the algorithms that are validated in the challenges. And eventually you could even make products out of pipelines of algorithms integrated in these web-based viewers. So this is reflected in the menu on the home page. We have archives, reader studies, challenges, algorithms, and eventually products. So now let's look at some of these algorithms that are available. I'm logged in under my account, so we see algorithms with a lock, meaning they're not publicly accessible, but there are also algorithms that are available to everybody. For example, this one for segmenting tissues in histopathology data. Now we're going to open pulmonary lobe segmentation, and this is an algorithm that we developed in the COVID-19 era to segment the lobes in CT scans of COVID-19 suspects. And we published this in IEEE Transactions on Medical Imaging. We put a link there, and now people from all over the world request access to use this algorithm. And they can upload scans, and they are then processed, and then you can actually open this in your web browser. So now we fire up a Docker container that contains a professional radiological web viewer. And it loads the data, and you can view it like a radiologist would do in a medical workstation in clinical routine. So in this case, a thorax abdomen CT scan was uploaded, and the algorithm has segmented the lungs and the lobes. And we can view it in different directions. Here we see the axial cross sections. We can also turn off the overlay if we want to inspect the data better. We can view in the sagittal, in the coronal direction. And now let me zoom in to the lungs, because we want to inspect the lung segmentation and the lobe segmentation here. And we see that we see the fissures. We can scroll through it, inspect the data. We have the tools that you have in a professional workstation, like you can use a maximum intensity projection, and then you see the vessels much better. And these are the kind of tools that radiologists are used to, and it takes a lot of processing power. That's why we run this server-based, so that people can view it in a web browser but don't have to do all the compute. So let me see, look at the scan. You see the fissures, and we can inspect if the segmentation of the lobes is accurate. It's pretty accurate in this case, and this way the radiologist can see the results of the algorithm on the data directly. And then the radiologist can also download the results, or download buttons, but he can also try it out for himself, choose files. In this case, I upload a scan from my own computer, and we support various file formats like DICOM and other popular formats. And when this scan is uploaded to S3, the user can submit it, and then the algorithm will be running on that scan that you have just uploaded. So first the imported images are checked for if it's valid input, and then the scan is placed in the queue, and when there's a spot available, the algorithm container is fired up and will start processing the data. And for this algorithm, it takes about 2 minutes to process. And now you see that the processing has started, so you'd have to wait for 2 minutes until you can see the results and download the results on your own computer. And this is not practical if you have thousands of scans, so we have a REST API access, so you can also have a Python interface to all the algorithms here. But then came COVID. In March, our hospital, and many hospitals in the Netherlands, were flooded with very sick patients. And we started to make CT scans, because the reference test for COVID-19 is a PCR test, but that PCR test took much too long. It could even take days, but certainly hours. And you need to decide immediately what to do with a very sick patient. Are you going to hospitalize him? And if so, are you going to send him to a COVID ward or to a regular ward? Or do you send them home? And therefore we would use CT to get a working diagnosis. And we also saw that many COVID patients, actually about 20%, initially had a negative PCR test. So that means that the virus is not present in their nose or in their throat, but they had all the symptoms of COVID. And in that case, you would use CT to clinically diagnose these individuals as COVID positive. And often later, the second or even third PCR test was then positive. And finally, CT is also very useful to quantify the amount or the severity of the disease, the amount of lung damage. And that's important to decide who you're going to put on oxygen and who you are going to admit to the ICU. Now, our radiologist, together with colleagues in the Netherlands, they quickly developed a scoring system describing how to report on CT scans of COVID suspects. We published this CORAD system in Radiology, which is the most important scientific journal in our field. And this publication is now the most viewed publication from the journal. CORADS is the reporting standard throughout the Netherlands and is used also in many other hospitals worldwide. And now our radiologists had two questions for us. Can you make a training tool to teach radiologists the CORAD system? And can you develop an AI algorithm that can process scans for sites where there are not enough trained radiologists available? So we decided to use Grand Challenge for this, and we created a reader study where any radiologist can practice with the CORADS reporting system. So you can open the study, you get some information, and then again you launch, like before, a web workstation which fires up and scans are loaded. And now in your browser you can inspect the CT scan like you would in clinical practice. So it loads the CT scan and you see these typical bilateral ground glass opacities that are typical for COVID-19 patients. And remember, every radiologist in the world had to learn this scoring system very quickly. So this teaching tool is very helpful there. You can look in different directions. In this case, you would say this is a CORADS 5, and then you would compare your answer with an expert panel who also scored it CORADS 5, and this was in fact a PCR positive patient. Then you can close that and you go to the next scan, and in this way you can quickly gain experience with reading these CT scans for this new disease. Now, apart from the training set, from this training tool, we also made our CORADS AI algorithm available. Radiologists can open cases here, and I made 10 cases publicly available from a public data set, so everybody can open the results and see the results of the AI algorithm that we have developed, and also upload their own data. So again, a container starts on AWS in the Frankfurt region, as that is the data center closest to my location. And the viewer has started, and we see the CT scan and the COVID regions in this darker color. So these have been segmented by the AI system, and these are the abnormalities associated with the disease. We can also see that in this scan, if we look in the coronal direction, that predominantly the lower lobes are affected. And that's also reflected in the CT severity score that you see here. So the CORADS score is 5, but you get per lobe a score of the amount of abnormalities, and then a number of points which say that this is a severe case of COVID, and you can use that in clinical decision making. But now we had a problem, because we published this CORADS algorithm also in Radiology, and we mentioned in our paper that the algorithm was freely accessible to everybody. And we saw a large number of users coming to our platform for the algorithm and for the reader study to practice CORADS. How to handle all this traffic? We needed a scalable solution, and that's why we reached out to AWS. And together with Razvan's team, our engineers managed to put grandchallenge.org entirely on AWS. We were already using AWS for some parts of our system, but now we moved over everything in only 2 months. And in the future, we want to use more services in the AWS ecosystem to further enhance the platform. And to show you how that works, I hand back to Raz.
Thank you, Professor Bram van Ginneken. So when you look at the grandchallenge.org and really at machine learning platforms in general, there are a set of challenges that we see over and over again. Users are spread across organizations and sometimes continents, and they need to collect, store, and access large amounts of data. securely, and with granular permission. The same users, including data scientists and researchers and clinicians, need to access the tools and applications from remote locations and multiple devices to be able to view, annotate, label, QA this data. And they also need integrated end-to-end machine learning pipelines to be able to train, evaluate, optimize, and deploy machine learning models. But today, machine learning is a team sport. So you need to collaborate. And you need to provide and manage reproducible environments across research teams and organizations. When you look at how medical imaging data is exchanged today, shipping hard drives across sites is rather the norm. With Amazon S3, you can use a scalable, available, and durable cloud storage service and implement the security and compliance controls you require, such as encryption or granular permission control. The team at Radboud uses S3 with accelerated transfers to gather data from sites around the world. Users are able to upload data in a variety of medical imaging formats, including DICOM and whole slide images. Viewers and interactive tools are core components of machine learning platforms. In medical imaging, those applications often require GPU acceleration for rendering and need to be highly responsive. The grandchallenge.org team deployed a full-fledged medical imaging workstation in 3 AWS regions: in Europe, North America, and Japan. They use GPU-accelerated EC2 instances and use autoscale and managed containers to scale horizontally. So as Professor Van Ginneken showed you, users can start on-demand workstations in less than 30 seconds. Load CT studies with about 500 slices in less than 10 seconds and have a highly interactive experience in the browser with less than 20 milliseconds latency. In a collaborative setting, oftentimes external researchers require access to data repositories that are stored off-premises. The Radboud team uses an architecture that includes AWS Batch for scheduling jobs, Amazon Elastic Container Service, Cognito, and the Identity and Access Management Service to enforce access control. And as a result, external researchers can train machine learning models on large datasets off-premises, while the appropriate security mechanisms are in place to avoid data leakages. Now let's switch gears and ask ourselves, how does this all apply not just to research, but also enterprise imaging? Our customers tell us that they are concerned about increased cost of storage as the data grows in volume, variety, and velocity. They are also challenged to ensure business continuity and provide highly available infrastructures. And today, more than ever before, that infrastructure goes beyond the premises of an organization and extends all the way to people's homes, as an increased amount of work is performed remotely. And many are looking for ways to leverage AI, ML, and analytics. And certainly, the majority is focused on strengthening their security posture. The first thing to address is the storage of data in the cloud. This can be achieved with S3 as a highly durable hyperscale storage service. And with S3, you can also cost optimize with automated data lifecycle management by leveraging various storage tiers, such as infrequent access and Glacier. Services like Storage Gateway and Direct Connect and Snowball make data transfer into and from the cloud easy to implement. With your data now in the cloud, you can start thinking about running highly available infrastructures and deployments of zero-footprint applications. The possibilities are vast, starting from disaster recovery with increased availability and reliability using Pilot Light or hot standby architectures, to VDI solutions, or deployments of PACS and RIS applications in the cloud to enable working from home and teleradiology. And you can choose from a large variety of compute instances and the largest managed container services offering for the deployment. Well, you will say, that's great, but what comes after taking advantage of cloud storage and running highly available infrastructures and legacy applications in the cloud? Well, next is the new world of modern applications built on microservice architectures, serverless technologies, and state-of-the-art AI and ML analytics services. Now you can build your very own machine learning models and bring it from bench to bed with SageMaker, or deploy third-party machine learning models in clinical production with deep learning containers. You can increase the quality of clinical documentation and structure your data with NLP services such as Amazon Comprehend and Amazon Transcribe Medical. And you can leverage analytics pipelines for your operations to become more measurable, optimized, and predictable. And I'm glad to say today that some of our customers and partners are paving the way when it comes to transforming medical imaging workloads with machine learning on AWS. For example, GE Healthcare is using SageMaker to train AI applications for medical imaging and then deploy those applications on intelligent devices, at the edge and from the cloud. Arteris enables AI imaging with a cloud platform built on AWS, relying on services such as Amazon DynamoDB, Amazon EC2, EBS, and S3. To sum it up, as you think of transforming your medical imaging workloads, I want you to remember, first, the advantages of S3 hyperscale storage with optimized lifecycle that helps you save cost and implement the required security and compliance controls. The importance of running highly available infrastructures with capabilities of deploying zero-footprint applications. The opportunity to unlock value from data with AI and ML, and use analytics to drive decisions in your organizations. And I want you to think big and think global. And I do have a challenge for you. Think about what machine learning model would make the biggest impact on your organization, and get started today. And to help you with that challenge, I'll turn it back to Professor van Ginneken for an exciting announcement.
Yes, I'm happy to make an announcement here today that we will start a new COVID-19 classification challenge on grandchallenge.org. We will make a large amount of data available to develop AI solutions that should differentiate between COVID-19 CT scans and CT scans that show similar abnormalities but are not COVID-19, such as other types of pneumonia. We make our previously developed algorithms available so teams can build upon these existing solutions. And we will do this challenge in close collaboration with AWS, and we call upon the machine learning community to jointly develop solutions that can help in fighting this pandemic.
As you can see, we have several other healthcare sessions at reInvent, so please take the time and join those sessions that are interesting to you. Thank you very much, and please get in touch to talk about reinventing your medical imaging workloads on AWS.